You got it? Okay, I'll begin. Heavenly Father, we thank you for this day. We thank you for the snow melting so we can have class again. Just thank you for your mercy for us each and every day. Thank you that you loved us. Whether or not we love you, you still love us, Lord. And we thank you for that. We thank you for your grace and mercy for us each and every day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so maybe you guys have questions about the homework. I'll collect it tomorrow. Did I announce that to you guys? Okay. I all of a sudden, when teaching two sections of the same course, it's disconcerting slightly because, I'm not sure I sent the email to the other section. Because I got an email from some guy who's like, I'm sick, I don't want to turn the homework today. I'm like, which section are you in? Did I not send the announcement to the other section? I know I sent it to at least one section. So anyway, you guys go ahead and ask a question before I yammer around about nothing. 9.1, number 30. So what you got to do here actually is to break into cases. Did you ask me about this one before? I was addressing a totally different problem when I gave you advice. I thought you were asking me about. There's a related problem to this. This is not the problem which you guys are asking me about, but a related problem is this one. For A, B, C greater than 0, and it's not A, B, C greater than 0. It's AC greater than 0. Right. That one. So if you look at that problem, which is physically relevant because that's basically like mass. I mean, that basically means that this differential equation matches an RLC circuit or a spring mass problem with damping. In those cases, you have bounded motion. There are three cases. You either have exponentials times sines and cosines, and then like t times an exponential. But the arguments in the exponential are all negative wherever they are, so those die to 0. And then the thing that you might not know, the thing you might face is something like this: e to the minus lambda t, and the limit as t goes to infinity of that. So that's the one thing for this problem that you don't have the technology for. Now the problem you're asking about, number 30, you just got to think about what are the solutions, right? I mean, you got what? Y prime prime, is it plus ry? Okay. So check this out. If r is greater than y prime?
Y prime plus ry.
Oh, well, that's not that exciting. Fine. Oh man, I want to talk about this problem. Fine. Well, then what's there to say? I mean, we can solve this by integrating factor method. The solution is generally y is equal to c1 e to the minus rt, right? And so analyze it for different cases. I mean, not much to this problem. Yeah?
I was able to do A and D.
Not B and D?
B and C.
Well, if r is less than 0, right? Then what's the limit as t goes to infinity? I mean, what's the... Is he using x or t here? He's using x. Let me use x. You said B and C you couldn't understand, right? So, all right. Okay, I'll come back and talk about that in a minute. So just to here's how I would start the solution. I'd say, okay, so y prime plus ry equals to 0 can be solved. You let the integrating factor h be the exponential of the integral of r dx, right? Which is e to the rx. Multiply this. We have e to the rx y prime plus r e to the rx y equals to 0, right? So this is ddx of e to the rx. In fact, I think we worked this before. So e to the rx times y is equal to c1, or c. We could just call it c. Why not? So y equals to c e to the minus rx, right? This is totally general. This does not depend on whether r is positive, negative, or 0, right? I mean, this is just a straight calculation. And then to answer those questions, you just have to think about the nature of the exponential function, right? I mean, why is this? That's always unbounded, right? Why is it always unbounded? I mean, if you think about the whole real line, if r is what? If r is positive, what's this look like? It's a decaying exponential, right? So it goes to 0 as x goes to infinity. But as x goes to minus infinity, you've got e to the minus minus, which is e to the plus, so it blows up, right? If r is greater than 0, it blows up to the left, then it asymptotically goes to 0 to the right. If r is less than 0, the reverse is true, right? If r is less than 0, this blows up as x goes to infinity, but it goes to 0 as x goes to minus infinity. So
How do you move from positive Rx to negative Rx in hypothetical?
solve. I mean, I multiply both sides of the equation by e to the minus rx. Yeah. Now, this is a. Oftentimes I ask this in the homework. I'm not sure if this is in your homework set. This is probably in your homework. If I found this problem, I likely put it in your homework set. Oh, okay. So this one here, there are 3 cases to think about. It's a little bit more written. Like that one's, there's one solution method that works for all cases. And you're just analyzing different behavior of exponential functions in parts B, C, and D, right? I'll leave that to you guys. I mean, there's really not much more to say except, I mean, the solution for B and C and D really just comes from looking at this equation and just saying common sense things about how exponentials behave. I don't want to make it more formal than that. I guess I could make you go back to Calculus 1 and prove it's this and that and the other thing, but I'd really like us to just have this agreement with one another that we know what exponential functions are and we can quote their basic properties. You don't want me to be more formal about that, do you? I mean, I don't want to be more formal about that. This is not a course in real analysis. I mean, it is, but it's not that course. All right, so this one, there are 3 different cases, though, you see. You could have stuff like e to the what? Lambda 1t, e to the lambda 2t. There's the middle case. There's the e to the lambda t, te to the lambda t, right? And then there's the e to the alpha t, sine beta t, e to the alpha t, cosine beta t. So for this corresponding problem, like analyze the possible solution structures in this case and show that as time goes to infinity, they all are bounded, right? Well, as time goes to infinity, you can show that these are in fact bounded because, like, when you work it out, given this condition A and C be positive, it forces lambda 1 and lambda 2 to be negative. And it forces lambda to be negative, and it forces alpha to be negative. Or at worst, it could be 0. If alpha is equal to 0, you get sines and cosines. Those don't blow up to infinity as time goes to infinity, right? And then the only thing that's kind of in question here is this term right here. That you might not have the analytical tools to deal with. So to take care of that problem, this is what, as t goes to infinity, this is what kind of limit? Infinity times what? What does e to the lambda t go to? supposing lambda is less than 0. E lambda t does what? It goes to 0, right? So this is type infinity times 0. That's an indeterminate form, as we'll be talking more about soon. And so the way to do this one, and sorry, I guess I'm giving you advice about homework 5, but you can forgive me, right? I mean, you'll be doing that one soon enough, right? So you rewrite it like that, and then you can use something called L'Hopital's rule. So I'm giving you this for free for the next homework, because we haven't covered L'Hopital's rule yet, right? So L'Hopital's rule, type infinity over infinity, the way L'Hopital's rule works is you differentiate the top and the bottom separately. Assuming, now it has to have type infinity over infinity or 0 over 0. In these two cases, these two indeterminate quotients, let's say, L'Hopital's rule says the limit of the quotient is the same as the limit of the derivative. But it's not the derivative of the quotient, it's the derivative of the numerator divided by the derivative of the denominator. So you separately differentiate the top and the bottom, which is nice, right? Because this is 1 like that by the chain rule, right? And so we get what? 0, right? So moral of the story, exponential wins. And even in the case you have t times exponential, that still dies to 0 pretty fast, even in that critically damped case. All right, I will stop talking about your next homework since you have questions about your current homework that's due tomorrow, right?
It's B and C. Under the top equation.
B?
Yeah.
What? Really?
Yeah, because there's no A in the problem.
Oh. Oh, if b is greater than 0, then one of the cases I talked about is even gone. I mean, if b is greater than 0, the pure sine, pure cosine case is ruled out. I mentioned sine and cosine were solutions. That assumes that b equal to 0 is a possibility, because sine and cosine are solutions to like this one. So, sorry, I'm giving you advice about a more general problem. You can just ignore my A, basically. The same advice goes through. But for you, no sine and cosine, because those are those are the ones that come from B. You said it's called B, or is it called A?
Well, they call it A and B, but
Oh, okay. So the meanings have been flip-flopped. But basically, if the coefficient of y prime can be 0, you end up with pure sine and cosine solutions, which are also unbounded. So that problem is trying to be nice to you guys and eliminate that case of the analysis, which is kind of unfortunate because that case in the analysis is important for applications. Okay. Anyway, I shut up about that. Can I erase before I distract you guys further? Or? Well, I'm going to erase. So you have more questions about homework? What are we, homework 4, is it? Oh, by the way, don't worry, I'm not going to give a quiz today. I'll probably give one Monday next week. So, let's see here, 23?
On the same things, the first, like, the quiz will still be on.
On the test, on test 1 material. Yep. With definitely no numerical integration. Let's see here. Where are we? Problem 23? Oh, 9.2.
Yeah.
Okay. Yeah, 23, 9.1 looked like fun. Let's see here. So what's the question?
Well, so like I did like the differentiation and stuff,
Mm-hmm.
but I got to an answer, like since there's 2 B's in it, I can't eliminate both for part A.
Okay. So I guess what I would tell you is you have to, work out the integration here. So we got what, dv dt? Oh, sorry, m, yeah. Was it minus alpha v?
yes.
Minus beta what?
Beta B
v squared. All right. My inclination here, because I dislike minuses, is to rewrite this as follows. This is dv divided by alpha v plus beta v squared, right? And that's equal to minus dt over m. And now I've separated variables and integrate, right? This is definitely not an integrating factor technique because this is not a what? This is not a linear ODE, right? Because of the, in particular, this term right here, right? So that's, if that wasn't present, I would have just linear appearance of the derivative and the dependent variable. But that v squared term means it's nonlinear, which means I can't use integrating factor technique. I have to use our other technique. We only have two. So process of elimination, it's got to be separation of variables, right? Then how do you integrate those? Well, I can do the easy part. This part I can do. There you go, for free. We'll add the constant over here. But the other side, what? How do you integrate that? Indeed. So what we have to figure out is we've got 1 over alpha v plus beta v squared, which, let's see here, we could rewrite that as 1 over what? Alpha times v, 1 plus, oops, goodness gracious. I mean, there's different ways you could go here. I'm going to say 1 plus what?
Wouldn't it just be the DL?
Oh, I mean, fine, if that's what you want. V times alpha plus beta. So you want me to do it like that?
Oh, well,
I mean, you got choices. You could write it like this. You could write it like this. Oh, excuse me. What do you guys want? I mean, it doesn't, pick your poison. We can go partial fractions on either one. It's really just a question of the second one? All right. It goes against my natural hatred of fractions. So all you got to do is find a over v plus what? B over v plus alpha over beta. And I'll tell you what, instead of using b, I'm going to use a c here just in the interest of not confusing with my beta. Why? No, I mean, that's not how it works. You could do like this if it's more clear to you. I mean, you could do that if you want. That would just your a would not be my a. Your a would be my a times beta or something. So it's just it's a question of nomenclature, really. And then you go from there, partial fractions, right? All right, so I'll let you guys figure out the a and the c, all right? But eventually you've got what? Integral of a over v plus c over v plus alpha over beta, right? dv. Again, algebra will actually, you'll be able to figure out specific a and c here, right? Work it out. And what you get then, of course, is natural log absolute value v times a, right? Plus c times the natural log of the absolute value of v plus alpha over beta is equal to what? Minus t over m plus this constant of integration, c1. And then what do you got to do? It says find v as a function of time, right? So you got to take all this, right? And you got to solve this for v. which you can do by properties of the exponential and such. I mean, I did it. It's possible. Just now, and then what you can do, of course, is you can set v of 0 equal to v naught, and then you'll be able to trade this c1 in the solution for like a v naught when you work it out. Alternatively, of course, if you want to build v naught into the solution from the get-go, what you could do would be something like this, right? You could integrate this from, say, v naught. I could put some bars on here like this, you know? And I could integrate from v naught to v. Or I'll tell you what, let me do this. I could integrate this from, say, v naught to v1, and that would give me a formula in terms of v1 and v naught. And correspondingly, I can integrate t from, say, 0 to t and final, let's say t1. And that would give me, t1 over here. And then once you're done with the calculation, after everything is done, you can just set v1 equals to v, and that will give you the solution written in terms of v naught. That's another way you could build the initial velocity into the formula without having to. I mean, you got two choices. You can either integrate from time 0 to time, time 1, and then later say v1 is equal to v. That would give you a formula of v in terms of v naught. Or alternatively, you can just integrate and then fit the constant c1 to time 0, and the knowledge that when I put in time 0, I have to put v naught here because that's the initial velocity. So I mean, you have these two different ways of finding the solution in terms of v naught, but I'm not sure which one would be easier. Anyway, is that helpful? I mean, I think you were stuck on the integration maybe. But.
No, I got through all that.
Oh, okay.
I was stuck on the solving for v.
Okay, what'd you get? I can help you with. I mean, what did you get for, so you got through to this part. What did you get?
Well, I did it like second right equation in. I did it like that.
That one?
And so, like for my A and B values,
Mm-hmm.
I got 1 over alpha, and then for A, and then B.
So yeah, so you have 1 over alpha v, is that right? And then what's the other thing?
Negative beta alpha.
Is that upstairs or downstairs?
Negative beta over alpha.
Oh, okay, negative beta over alpha. And that's times what? Times the alpha plus beta v
Yes.
for you? So that's what this is equal to that. Is that right? All right, let me just check you on that real quick. Okay, so that's, if I make a common denominator, let's see here, I can just factor the alpha out, right?
Yeah.
So if I make a common denominator then, that would give me alpha plus beta v, and then over here minus beta v. Perfect. Yeah, you're right. Very good, very good. Partial fractions is spot on. So I integrate this, I get 1 over alpha, natural log the absolute value of v, minus, well, hey, that's pretty cool. So, like this is easier to think about if we divide by beta. Well, I don't know, I mean, you just left, I mean, what did you do? Well, let me just write it.
I did like a u substitution
Mm-hmm.
for alpha plus beta v. So then my like I had du equals beta dv, so the beta is canceled.
Right.
And then it was 1 over alpha.
Right. So it's that. I mean, this is out front, right?
Yeah.
Okay. So you got this is equal to
The negative t over m.
t over m. Yeah. Look, this can be simplified, right? This is really the natural log of the absolute value of v over alpha plus beta v equals minus alpha t over m plus, let's say, c1 tilde. Whatever. So you exponentiate both sides, you're off to the races, right? If I exponentiate both sides, then I get the absolute value of v over alpha plus beta v is equal to what? E to the c1 tilde e to the minus alpha t over m. To get rid of the absolute value then, I got v over alpha plus beta v is equal to plus or minus e to the c1 tilde e to the minus alpha t over m, right? By the way, there's a calculation like this in my posted notes for the solution of the logistic equation. If you want to see a similar song and dance, there I find a solution that the logistic equation's almost the same problem. You have to use partial fractions there too, and blah, blah, blah. And now I got to solve for v. So, of course, you can say this is something. I mean, I guess I can just call this what, like big C, just because it gives me no joy to write plus or minus an exponential to a c tilde. So just call that thing c and go from there. Can you solve that for v?
That's where we get stuck.
Oh, really? Well, you're almost home.
Yeah, I know.
This isn't bad. This part, I mean, you just multiply that to the other side and isolate v. Your goal is to isolate v, right? So just subtract this to the other side and then factor what is the coefficient out. And if I do any more, I've solved it. But sorry to waste your time with the partial fractions. However, while your time may have been wasted, I'm quite certain that there are many others here who benefited from seeing this idea, right? I didn't happen upon an example like this in our lectures in this section, so it's good to talk about this because the separation of variables doesn't have to be an easy integration, right? It can involve one of our techniques that some of us understand. By the way, at any stage here, at any step in this game, you can plug in times 0 and find an equation. Like, I don't know if this is helpful or not, but just for fun, it would be true that v naught, right, would be equal to c times alpha plus beta v naught. See, because if I put t equals to t naught, t equals to 0, v is equal to v naught, right? So at any stage in the game, you can put t equal to 0, and that will relate. This actually gives you the form. I mean, you can find the formula for c here pretty easy. Right, c is going to be v naught divided by alpha plus beta v naught. So when you're doing part C, you could use that on top of the algebra, which I haven't written out. Yeah, I think I think that the by the way, the velocity problems in this homework are easily 4 or 5 times harder than anything else I've asked you, right? Do you think? I mean, they actually have some pretty tough algebra in them as things go. Other questions? No? All right. Go for it.
On 28, this was like in the exercise, page 466.
Oh, the orthogonal trajectory question, yeah. Mm-hmm.
So I was doing like geometry, and like you take the derivative of both sides, and then you kind of make your way down, and then you take the reverse reciprocal.
Mm-hmm. Here, I'll do a very similar but different problem. Notice the cube. Your problem has square. Okay, so we're supposed to find, this is a family of curves, right? This is a family. Why is it a family of curves? As you vary through C, you get different curves, right? Whoa. Now the one you have is very nice. 1 plus x squared. 1 plus x squared is very, very simple because 1 plus x squared is always greater than 1. So like c equals 1 over x squared, I can actually graph those for you. If that's a square, then like c equals to 0 is this, right? And then it does something like this. I mean, roughly speaking, this is y equals to c over 1 plus x squared. which is, that's the problem you're asked about. That's very different, see, because this is never 0. If I was so foolish as to try to graph these just for kicks, well, x equals to -1 is very troubling. So something weird happens with the solution set at x equals to -1. It's a common asymptote to all those solutions. All right. Anyway, let's find the orthogonal trajectories to that family. So what we do is, now the way I packaged this problem to you guys before, I took a slightly different starting point, right? When I talked about orthogonal trajectories in here before, I said, well, you're given a differential equation, right? I described a family of curves by a given differential equation. I just said you take that differential equation and you find minus the reciprocal of the differential equation and you solve that. That gives you the orthogonal trajectories. Where's the differential equation here, right? That's the question. Well, there's not one yet. So to find a differential equation from a given family of curves, you just differentiate. In other words, you go back to Calc 1, you do implicit differentiation and look at it as a way to create a differential equation. So this gives me dy dx is equal to what? Well, yeah, minus c over what? 1 plus x cubed squared times what? Three x squared, right? By the chain rule. All right, so far so good. And but there's this c, right? Man, I've gotten so confused about what to do about that c in like previous times I've taught this course, and it's really so embarrassing in retrospect because it's so simple what you do. Okay, so what do you do? Just go back to our starting point, right? Solve for c. c is equal to what? So I do and so then I've got myself a differential equation. I got myself dy dx is equal to what? Minus 3x squared y divided by what? 1 plus x cubed. Not squared anymore because one of them canceled, right? Now this is a differential equation whose solution set is the family of curves that we started with. Does that make sense? You guys with me so far? Nothing to do with orthogonal trajectories so far. This is just a differential equation which takes the original family as a solution set. To find the orthogonal trajectories, then, I do what I told you guys about before. I do negative the reciprocal of the slope. So to find orthogonal trajectories, I want to solve not this equation, not this differential equation, but this corresponding one. And I'll write it in the dumbest, clumsiest way I can, just to emphasize what conceptually is going on here. I'm doing negative the reciprocal of the slope. That gives me orthogonal perpendicular line, right? Locally. Perpendicular tangent line. And then you clean this up, right? This gives you what? Now we're off to the races. We've got a differential equation. It's separable. We can separate variables, integrate, solve it. I think. I may regret this. Let's see here. What does this give us? This gives us separating variables. What do you have? Yeah, y dy. That's not too bad. Equals what? One plus x cubed, right? Divided by 3x squared for me. Oh, that's not too bad either. So what do you do there? Oh, no. U substitution is incorrect. You divide, yeah. We do algebra. This is the integral of 1/3 x to the minus 2 plus 1/3 x dx, because if I have like 3 plus 5/18, it's 3/18 plus 5/18. You know, I mean, This is fractions. The addition in the numerator you can break up. So that's what? That's minus 1 over 3x plus 1/6 x squared, and that's equal to 1/2 y squared plus a constant. And there you go. This solution set to this family here is the orthogonal trajectories to the given family that I made up. So you can go through the same thought process to solve that problem. Yeah. Somehow hidden in this, I expect, there must be somehow hidden in this, like intuitively speaking, I expect that this also doesn't make sense for x equals to minus 1. Like something funny happens at x equal minus 1 at least. I wonder what it is. I really want to plot both of these and see what they look like. I will behave. You guys have other questions? Just looking ahead, guys, we're not in chapter 10 next. Where are we? Chapter 11, right? So tomorrow we'll be talking about the what? The least upper bound axiom, properties of real numbers, starting into our discussion of sequences. So, I mean, this course takes a pretty dramatic turn tomorrow. We're not doing calculations, we're doing theory for quite a while. So prepare yourself. I would suggest reading ahead would be a good idea. Yes, sir. 24. Which section? What about it? I mean, if you follow the instructions here, it's not too bad. Basically, the B, part B, and you've already done A? You've already done part A? So you should have something, if you look at it, you should have something like natural log of the absolute value, I believe, of VC minus V over VC plus V, yeah? And then some number out here equals to, I forget what goes over here. Just T. From A you've got that, right? So again, it's this algebra. Divide by the number, exponentiate both sides, isolate V. Now, if you don't have this already, maybe you have something like 1 plus V over VC over 1 minus V over VC. I would encourage you to take this, multiply the top and the bottom by the critical velocity. It makes it prettier like that, I think. You know what I'm talking about?
What about V2?
What about it? I don't see anything here about. Oh yes, the initial velocity. Well, that should be wrapped up in a constant somewhere in here. I don't know. I wouldn't know without like getting into the whole thing. Let me just. What's the original problem? Was it m dv dt equals what? Say again? mv minus beta v squared? Oh, mg. Okay. That's fine. So I have dv divided by g minus beta over m v squared equals to dt. No, fine. Yeah. Un momento. We do this here. Oh my God. Let's see here. You want things in terms of that critical velocity, right? Which is what, mg over beta? So if I can rewrite this as dv over 1 minus beta over mg v squared equal to g dt. Put g over there. Divide by g to be fair. Then this is dv over 1 minus v over vc squared. And then the simplest way to obtain an expression from v naught is, well, integrate this from, say, v naught to v1. Integrate this from, say, time 0 to time t, 1. Do this integration, and then you set v1 equals to v afterwards, and that should give you an equation between the velocity and the initial velocity as well as the critical time and all that. It's hard for me to say what you should do without looking at your calculation. But that's one way you could build the velocity into the equation to start with. Just integrate over corresponding ranges. And if you use the inverse hyperbolic tangent solution, you probably want to rewrite it as a log. Because it's like this. You should have something, not this exactly, but something kind of like this. So to solve that, you take the exponential of both sides, and then you isolate v, and then solve for v. Something like that. So again, tomorrow we will start into chapter 11, which is a bold new world. Oh, I should give you back your test before I forget. So I will say this. If you have a score which is like less than 30, you're in big trouble, frankly. And you really need to work harder, or you need to drop the course. Now, the reason you have that score, it may have nothing to do with work you're doing right now. It may just be where you started in this course, and that is unfortunate. But it is a fact of, well, you can hit the